Hi Ayush.
Good evening, ma'am.
Yeah, good evening. So probably today we'll do the week 9. I see that the assignment has been released for that. I was not well, so hence postponed the session of Tuesday to Saturday. And also it was holy, so thought that okay, let's give some time. So you have already solved that assignment, right? And the solutions for the
Yes,
same
ma'am.
have yes. So what I'll do is now what will be done through the corresponding lectures is that firstly you'll have some lectures and then followed by it would be some tutorials. Tutorials would essentially mean the MATLAB program, that how to implement it. But in the exam, no such program would be asked, but its implementation or say a code chunk would be given and then would be told to you that okay, what its following outcome would be, or would be something that okay, you have to implement so and so, so what sort of chunks can you use to do that. So options would be the same. So now what we'll do is that we'll take lectures in one live session and the tutorials in the other live session. So that's what I have planned for now. And so it's like sir had 2 lectures and 3 or say tutorials for week 9. Similarly, for week 10 also it's the same. So now we'll do all the coding sessions in one time and all the lectures in one time, so that it's like equal segregation. If needed, we can also go back to the theory when in tutorial it's required. Next thing is probably April 24 or 22nd is when the course ends. So we'll have a extra session on 18th or say 11th of April. Date of that hasn't been decided yet, but I have given my slots and they'll confirm. So accordingly, I'll need is like who all sees this video and also you Ayush who's present over here to give an approximate idea that what you guys want to learn, or I'll just go through the previous assignments of questions that have been done through now, or something that has been asked in the final exams, so that you guys have as like a pre-exam kind of thing. So we'll be doing that part also. So for week 9, I saw that there was ARMA modeling and then followed by the 2 tutorials. So I'll just go through the brief of how ARMA modeling was, the pole zero equations, Shanks model, and then the it's like previous year assignments. Okay. So are you have any questions, no, right?
Ma'am, I have one question. Ma'am, like in assignment, there was a question to calculate the Butterworth filter coefficients.
Hmm.
For that, ma'am, there is no mathematical formula. We have to write the code in MATLAB. So in
Mm-hmm.
exam also, will they give the compiler MATLAB compiler to calculate?
No. Nothing is like so far. I haven't seen such questions to be asked in NPTEL. But if it is like that, then they'll give the compiler. But what they expect is that you should know how to implement it in MATLAB. It was just to give you an hands-on. So if you know how to implement it, that's it. Or else you can do some math and solve it up. But for this order implementation and find the frequency and all, I don't think so that would be asked upon. So we'll go with the ARMA modeling then. So I've only covered the ARMA modeling. It's around 15-20 slides, and then the pre-assignment questions. It's much more similar to the ones that were given to you this time. So here we go. So now what the people are trying to do is that we have something in the linear regime. Okay, sorry. I hope the context is is that okay, what we are trying to do is that we were trying to predict something in the future by using the values in the past and present. And for the same, we were trying to model something. Now, while we were are trying to model some equations or our data just because we wanted it to show some trends. Now, if that we always won't need to like fit our data into some model. If we do so, then it would be sometimes it would lead to underestimation or it can be an overestimation. Now, to prevent the same, we need to know that what the nature of our data is, how it follows along, and if we don't know about it, then we need to model our data, or we need to see some standard models which might allow us to is like play some tricks or equations here and there so that we know that how our data is. So here is the pole zero modeling or the ARMA modeling, that is autoregression moving average model. Essentially, autoregression will give you how the data is being varied with, say, it's linearly with respect to the present and past values, whereas moving average is something that you take some windows and within that particular window, you do the average of all the data across the time series and then take out. So for the same, the general equation of pole zero model is that like this, where we saw that one was associated with the gain, other is the autocorrelation coefficient, and one essentially the characteristic coefficient of it. So they saw that, okay, if you have to see the frequency response of the function, so it can be modeled as an Fourier transform of the impulse response of the function, which is nothing but the gain square is nothing but this particular y part divided by the x part. So we see that, okay, this is like this, and which can be written as the Fourier transform of this particular function and this. So this S of B, S subscript of B of omega and SA of omega is nothing but the power spectral density. So how do we find the power spectral density? Is nothing but by taking the Fourier transform of the function and squaring it. So we do the same. How do we find the Fourier transform of a function? Is that coefficient times of e raised to minus j omega t. So we have this taking a finite duration, so we have our interval of the window from k equals to 1 to p. Similarly, that we have done for sp of omega. So then we need to find that, okay, what the total spectral matching error would be. So how do we, I guess something's missing. Oh, no. So how do we find the total spectral matching error? So we need to minimize this error. We need to find this factor in a way. So this is also represented in a way of power spectral density wala factor. So what we do is like take the Fourier transform and then square it. But instead over here, we have the value of it. Now, how can we represent it is there's no intuitive value or definition behind this, but the error over here, they gave it as the function, the entire function sy of omega itself divided by the impulse response of the function of the whole square. So this essentially tells you that, okay, if you have something and if you divide it by the impulse response of the function of the system, then essentially your error becomes independent of the system, and then you can always try to minimize it whatsoever the system would be. And then similarly, they say that, okay, we can represent this h of omega as SA of omega and SP of omega. So then we need to find some parameters to tune it so that it minimizes the error. So for the same, we need to know that how to compute this. So now over here, SA of omega and SB of omega, what will happen if you partially derive these two factors? Because since both of them are inside the integral, so we need to know which factors are independent of it. So we find the partial derivative of this particular divided by its AI coefficient. Similarly, this by its VI coefficient. Now, how do we get this? Is that if you see, is A of omega is essentially 1 plus summation of AK and exponential. Take a partial derivative, it would be 2 times of this whole, and then take the derivative of this. So we know e raised to minus j omega, so it will lead to cos term, and would be something like e raised to plus j omega plus e raised to minus j omega by omega or j omega. So we get this term. Similarly, for this, we also have this term. Now we notice over here that here our value is like here it was always minus jk omega, but now here it is I minus k times omega. Why so? Because now our limit starts from 0, whereas here it started from 1. Same difference. Next, so now they say that, okay, let's take a term is like a variable, say phi, where phi alpha beta is given by this 1 by 2 pi this. Now here alpha and beta are the corresponding powers for this, your power spectral density of the A function and for that of the B function, times cos of I omega d omega. So what we see that if both the alpha and beta are 0 0, then we see that this is the inverse Fourier transform of sy of omega, and hence simply that is phi of y of I. So here it's nothing but 1 by 2 pi, a definite interval, and then your function times d omega. So it's essentially the inverse Fourier transform. Okay. So then we also take the partial derivative of our error function here. So first we'll take it with respect to this first function, and then we'll take it with respect to this function. That is nothing but principle of superposition. So follow it along, and something we get is like this. So 2 times of ak phi of like this 1 and that to be 0. Considering we only took it with respect to ai, if it was bi, then it would be 0 1 and then I minus k, and the same interval that we have for I. And the same manner we have it for bi. Okay. So now we saw over here that this particular function that we have inside, it is not a function of ak, and we can get still a set of linear equation if we substitute the value as 0. But hence the coefficient ak could be calculated as in case of the ARMA model. So from the autoregressive model, we can compute this ak because that essentially is a coefficient over there. Okay. So then what happens if it's like this one? This will lead to a BL, which correspondingly leads to a set of nonlinear equation. Why nonlinear equation? Because it varies accordingly from this to this factor. So to get a particular model, now we need to solve some P linear equations and then a Q nonlinear equations. How do we do so? This like we have two separate independent parameters. So what we do is like follow the principle of superposition here also. So take one source, for solve for that particular source, take another source, solve for that particular source. For it's like till now it's clear.
Yes, ma'am.
Okay. So then how do we find it? Is that what we'll do is that we'll iterate the values again and again so as to see that where it optimizes and at what particular value we have the optimal solution. So probably you might be familiar with this Newton-Raphson method. It's a numerical method. So comes in probably maths 4 or maths 5. So we just have, is it apart from doing integration or differentiation directly, this particular method has some formulas. You iterate it. There are I plus 1 and so factors. So you get, so there's a defined formula for it. If you don't know, you can just Google it around. So this model, now we say that, okay, A is a vector of such vectors. We took a transpose of it. Similarly, we took a transpose of this too. Now, why did we took a transpose here? When you try to implement something in MATLAB or Python, in the X direction, you always have a limit of taking the number of iterations or taking number of values. But in the Y direction, if it's in a vector, you can take it and extend it along so many values that you want, or to accordingly to the sampling intervals also. So hence always whenever people take some vectors, they always assume or say that these vectors are nothing but column vectors. Okay, so they say over here that these are nothing but our model coefficients in a vector form, and the vector at iteration is like some m plus 1, and that is derived by this iteration. So here this is a Hessian matrix, where this Hessian matrix is like it has a particular its own definition, that it is second partial derivative order of phi, this error, divided by this C that was varying and times of C transpose factor. So this two will essentially cancel out when you have a symmetric matrix or a diagonally symmetric matrix. If not, then you'll always have to see that what particular value comes and then update the value over here. So the vector C again can be partitioned as these two vectors that you had, A transpose and B transpose, that we had over here. So A1 to this, similarly A, B to here. So then we saw that the iterative operation can also be written as this. So this was our initial value that we had, and then this can be first A, here BB, then AB, and then BA. So we had the values at each and every values. Oh, sorry. We can also determine the values for each and every coefficient and then keep on iterating it. So why did we do so? Is that if our model is not linear or a linear model won't always depend upon the initial values, whereas non-linear does depend upon initial values. So its values will always is like surround and surround, or its global minima, maxima will always go around its initial values. If you have given it some initial values, the model will always try to see that something where the error will become minimum, or if it's even 0 or the loss is 0 for your model, it should be around the initial value. If it's not around the initial value, it assumes that it's not fitting the data properly. So that is how this nonlinear equations and methods work like. So there are also a couple of statistical distributions. So in those statistical distributions also we need to enter some initial values, and after doing those initial, say the initial values for some models are like median and mode of the function. Now if you give the median and mode of the histogram function and then try to fit the function again by giving it some initial values, then the final value is almost as near to as your initial value that you gave. So essentially this particular part is more important, and when you also substitute the values too. So then they have characterized for all the equations, they took the partial derivatives for them. So this is nothing but taking indexing all the values. Again, when you try to implement this in code would be somehow hectic, but it's just that you need to write the formula and see how the for loops occur. So this will occur, but the initial estimate is close to the optimal model. So this is how this entire statement we always see in terms of wherever we are trying to solve the nonlinear models or nonlinear equations. But then it was something that, okay, if we take initial values, what we get is essentially near the essential values. So someone named as Shanti estimated it's like proposed this method as sequential estimation of poles and zeros. So he said that, okay, let's take this model as where your gain is 1. So gain would be fluctuated more because essentially this value is in our hand. It's like we change it, seeing how our signal is, or if you are not able to get the exact value of the signal, then only we change it. So it's fine if we take gain equals to 1. Let's see what effect does it give us. So now here what he's trying to do is that he is going into the Z transform method and is essentially trying to minimize the values in the numerator, in the denominator, and later going into the numerator. So that is how his idea was. So what he sees that, okay, if this yz can be written as vz times of tc, and then vz can also be written as xz by az, so they get ma part of the system as like this. So it's essentially varying. So what we saw initially is like take the function, delay it, and then add it, multiply it by the weight added, multiply by the weight added. Similarly for AK also we have the same, but then we add the initial value to it also, because this is essentially your part of the ARMA model or the autoregressive model, AR model. When you substitute the yn as that of hn, that is nothing but the of the input impulse of your function or the system, that's a delta function for the model, then something you get is like this. Now this was your function, so here we differentiated by delta model, whereas this was your entire function, that is y of n, so you represented it by the impulse function. So h of n can also be written like this, where, okay, this also starts from k equals to 1 to p, and here the number of terms that we have is nothing but are greater than q. So p is, now don't differentiate, it's like confuse in between p and q over here. Initially p and q were two different window sets of our functions, one for this, one for this. Now here our window is still 1 to p, whereas order of our function is nothing but something that is greater than q, some integer that's greater than q. So here both of them are not associated in terms of the windows of the duration of the function. Then they try and multiply it with the delayed impulse response of the function, and they see that, okay, something that we got is now similar to the previous values that we got, and we can again model the same system again. So now by taking gain equals to 1, we'll be able to minimize the solution. Also, it won't be that dependent upon the initial value. So now it's always computed independently of PL. We don't no longer have that particular term, and there would be the error, but it would be arrived after minimizing the error. Okay, so then for the error also, they also see that, okay, error is the total square error, so the square of that particular error and impulse function times of this autoregressive function. So we no longer have the BL term that was like adding a part or contributing towards a nonlinear function or nonlinear characteristics to our system. So using the same, then they characterize the AR part is that taking the denominator part, so that we had is this, and then solving for its error, so squaring for the entire term, where this is an impulse response of the function, that was essentially the inverse of the function. They minimized it, and then they saw that, okay, this particular function, this phi of h v tilde lj can be represented as the multiplication of two terms. But then here now what we see is that this impulse response is always multiplied to the function that is inverse of our entire is like autoregressive function that we had initially. So now we have eliminated entire nonlinear part from our function. So I guess, oh, it was it. So that's it. So we eliminated everything, and Shank's method was something that gave us an approximation that, okay, if we don't want our values near to initial values, we can do something like this. But given a point that this kind of method is computationally intensive, so people no longer try this method. They always go with the initial method that we have, is like having the values and then iterating it, see how estimates would vary. If not, then they will try to do this. But then again, here, if you do set or gain approximately equals to 1, then that it's like restricts your function and input to not take an advantage of the system to change it, vary it, say where your local maximize, where your global maximize. So it somehow restricts your functions. If anyone has a question, please do unmute yourself and let me know, or else we'll do the previous assignments and we'll be done. Any questions? Okay, if not, then we'll go into the previous year questions. For the people who joined us like just few minutes ago, for information, we were doing week 9. We decided that we'll be doing the lectures and the tutorials just like differently in 2 different sessions. So I'll be covering the theory first and then the implementation next. We'll be doing live implementation. So I'll be doing in my own system, and then you'll also follow me along. So you'll be doing in your own system, so that we get the hold of things, that how it's being done, and you are also be able to implement it. I know that you're also able to implement it. That's how what my job is like, to tell you and let you know that, okay, how it's actually going on and how it's also on mine. So that's what I have decided for now. And following weeks will have more of the tutorial sessions and less of this theoretical sessions. So theory, what all you needed to know till now is mostly covered, and till April 24 or 22nd is something that our course will end. So before that, we'll have an extra session. So if you want me to have some summary of the entire course, or do some tutorials or something, or more questions and assignments, do let me know, so that I'll prepare it accordingly, and something that would be beneficial for you. So we'll just do previous assignments for this week 9, whose solutions and assignment has already been solved by you guys. Now week 10 is something that we'll see on Tuesday, and probably it's due on Wednesday. I hope so. Okay. So here, we saw it just now. In Shank's method, the gain is considered as you all remember, right? Week 9.
One.
Hello?
Ma'am, gain is 1. B.
Yeah, yes. Then a notch filter is applied on ECG signal. So mostly now the questions would be something that you should solve. In the tutorial, when sir implemented those MATLAB assignments, he showed that how some of the things can be solved and then implemented. So you can take the examples of those to solve these questions, or also you might have solved for your assignments. So a notch filter is applied on an ECG signal that's sampled at 250 Hz. Huh?
B.
D option.
D option. Can you explain how did you do that?
Because the omega naught will be plus minus 2 pi f naught by fs, and plus minus 2 pi 50 by 250 is 72 degree.
Okay, so this is how 2 pi f naught by f is 50 by 250. Similarly, so you know how to do it in calculator, right? It's like conversion of radian to degrees. So that's something that I don't know. Probably you are not allowed to take your calculator with you, but in the exams you'll have a virtual
Put
calculator.
pi equals to 360 degree, you will get in
That's true. That's true. But sometimes the angles are quite complex. You don't get direct integer values. So just have a quick it's like idea that how do you convert it into virtual calculator. So NPTEL might give you an prox, it's like before the exam, that how would the interface would be, how the exams would be taken. So be familiar with the system also. Okay, so if poles are added in the notch filter, then within the unit circle the bandwidth becomes wider. Attenuation, what happens to attenuation? Okay, so keep in mind that poles are something that's in the numerator, and if it's within the unit circle, so it has to be stable. Then what will happen to the attenuation when it comes down, narrows down, and to the bandwidth also?
Ma'am, D option.
Becomes narrow, and attenuation at adjacent frequencies decreases. Yes. So this was through the tutorial solution of 1.1. Okay. And the poles in the notch filter located at this, then as R increases from this to this, what happens? So same question that we had just now, just have to see what those implications are.
B option.
decreases.
So it increases. Again, so it happens, if it happens flipped way around, what will happen?
A option.
Okay. A signal of frequency 100 Hz, so Nyquist rate with sample will correspond to time instant of 0.5 second. So the frequency is given, find the Nyquist rate for the same, and then with sample corresponds to 0.5 seconds. So convert it, it's like flip it and see what the value is.
C.
100. Yes. So frequency is 100, sampling is twice of the maximum frequency, and then you see that time instant line, output is 100. So how many samples will we have if your signal is sampled at 200 Hz? Okay. The representation of transfer function of the system is given by this. In MATLAB would be, okay, how do you define it? What do you say? It's like you give the coefficients and then you take the transfer function. So if you have to see the transfer function like this, how will you write it?
A.
Yes. So others get it?
Ma'am, please explain this one. 7.
Yeah, so you see that the coefficients are like this. So initially what we do is essentially write all the coefficients, taking the first one as the initial value. Now we don't have any, and then the constant at the last, and then your functions. Then similarly this particular function, and then the transfer function is taking the zeros and poles and inverse of the sampling frequency. So if you don't take inverse of the sampling frequency, essentially you'll be doing it, it's like applying in the frequency domain. Now you have to define it in the time domain first, and then it will convert. So transfer function is something that converts into frequency as you go for MATLAB. So that's how you do. It's fine.
Okay, ma'am.
Find the numerator polynomial B and denominator polynomial A coefficients for the Butterworth low-pass filter with cutoff frequency 50 Hz. Probably this can implement in MATLAB, I'm not so sure. Order 4 and sampling frequency 200 Hz. Try it. If not, then we'll have a look at the solution. Any idea? Yeah, probably the answer you'll get would be somehow like this. You'll have to write it. We didn't do that. How it would be in the MATLAB, something like this. But you can give me an idea that how will you write it in MATLAB? If you know. So for filter, we need to design what all parameters to be given MATLAB. If it was a normal impulse transfer function, we wrote it as the coefficient, sampling frequency, and the transfer function. That's it. Now, if you have to design a filter, then what all things are needed? First is the order of the filter, the sampling frequency, the center frequency, and then essentially you define the Butterworth filter. So just give an approximate idea how do you write so. That's it. Answers can be as like tallied afterwards, so it's fine if you don't get the exact answer.
Ma'am, first we will define sampling frequency, cutoff frequency, and order of the filter. Then there is a function butter. So we will write square bracket BA equal to butter, and we will pass the variables, and we will get the values of B and A.
Okay, so if it's a low pass filter, you do as low, and then if it's a high pass filter, you write it as high. And then how do you define the frequency? Do you directly give the cutoff frequency and sampling frequency, or do we do something to the frequency? That's a tricky part because whenever you have, yeah, go ahead.
Normalized version of cutoff frequency.
Yeah, yes, yes. Okay, so this is how we'll write the chunk of code, and then you'll get the values in there. Okay. So a signal is defined as.
The MATLAB interface
Yeah.
in the exam.
I don't. No. I don't think so. Something that would like be given because so far the exams that I've given didn't have a MATLAB compiler in them. If they do, it's like if they do expect something like this, then they'll give a compiler. If not, they'll just ask you that how will you write it, and then what accordingly the it's like the step of implementation would it. Or else they can just give you like this the step of implementation and will ask you that okay, what do you expect from this? That's how it's like, okay, if you have given like this, so what are you trying to do from it? So we're essentially trying to design this, something like that. They won't expect you to solve this mentally and then give the answers. Okay, next question. Signal is defined as x of n is this, and the signal is corrupted with noise with y of n. So what is the signal to noise ratio of y of n? So that's nothing but signal energy by noise energy. But then here it's defined in decibels. So you take 10 log 10 or 20 log 10. If it's in amplitude or if it's in power, the 10 and 20 terms varies. And then how do you find the noise over here? Is that this is your signal, this is something corrupted with noise. So this minus this part. So how will you write it? I don't want the answer again over here. You'll have to probably implement it in MATLAB, but just how will you do so?
No, ma'am, this question can be done with paper and pen also.
Yeah, if you want to solve, you can solve. It's like, for the sake of going ahead, I thought, okay, you can just let me know how will you solve it. That's it.
We will
And we
find
will
the
first to find the
noise with the help of corrupted noise and the signal. Y minus xn will give us the noise signal. And with the help of that, we know the formula of energy. Like we have to do the square and sum all of that. And by the help of SNR formula, like 10 log 10 signal upon noise, we get the answer in D.
Yeah, yes. So that's how we did. Yes, explained it very nicely. So noise is the corrupted signal with noise minus the signal, and then you have the formula for SNR, where this is both of these are energy, so you square them, and then within that particular interval. So here the interval is very finite, is like 0 to n number of terms. Take it, square it, divide it, you get the answer. Okay. If the signals are defined as this and this, then the maximum cross correlation of this and this is given by what? So shift it right, multiply it, add it, and see where the maximum value would be. So this is something very familiar to the first question that we had at week 0 or say week 1. So probably you all know that what autocorrelation, cross correlation was. So we have one equation, sorry, one system, or say one input, we have another input, and then you correlate both of them, and then you see that where the maximum energy would be, and that's how you shift it, delay it, advance it, and then multiply it and add it. You can also implement it as we do convolution in the matrix method. Add some values over here, write some values over here, multiply them diagonally, see the values across the final value.
Is it D?
So you multiply it and see that where the value was. This is across which index, can you say? So 0, 1, 2.
0.
Okay, that's it. Thanks for joining. If you have any doubts, let me know. Or else, now next we'll do the tutorial. Not that same tutorials, but we'll actually implement it. If you're not able to implement it, it's also fine. If you're able to implement it, it's also fine. You can also share your screen. I can also share my screen. We'll solve it on MATLAB and see that how the this varies. But for the same, probably when sir did, you guys didn't had access to those what do you say, the signals or value functions that he's using. We'll try to use some sample basic functions. I haven't figured it out how we'll do that. We'll see, or else we'll just try and see that how to implement basic filters and then how to see maximum energy, how to take envelope of a signal, all this basic kind of things we'll do. Probably this won't be that helpful to you for your exam point of view, but it would be helpful for hands-on, and say if you are trying to do signal processing or trying to save your career or your fine, it's like future degree in that would be helpful for you accordingly. So that's it from my end. If you have any questions, do stay back. If not, thanks for attending.
Thank you, ma'am.
Thanks.
Next problem session will be on
Tuesday.
which day? On every Tuesday it will be there.
Yeah, every Tuesday we have 6 to 8. This Tuesday also we had, but I was not well, so I postponed it to today.
Okay, ma'am. Thank you.
Thank you. Harsh, do you have any doubts? I guess not then. If you do have, let me know, or else I'll stop the session then. Thanks for joining.